Okay, this is part 2 of our exponential decay or growth models. The first 3 examples we looked at in part 1 were all decay models. The K, the growth or decay factor was negative, meaning it was a decay factor, things were getting smaller. I think these involve growth models. Let's see, these are examples about money, which is good, we want it to grow. And also bacteria, which can be good or bad depending on if you need bacteria or you don't want it. So anyway, the next problem, it doesn't have a number. I just typed that in on the worksheet. How long would it take an investment of $1,350 to triple if it's invested at a rate of 2.6% continuously? So continuously is a big key word here. Here is the continuous compound equation, and it is this. This is a money equation, and it says this. The amount in the account after some time t is equal to P, the initial amount of money invested, times E raised to the RT. Sometimes this is referred to as the PERT equation, but this is for continuous compounding. So, what is the difference? Because we've had compound interest equation before, but before we had an extra variable called n, which is when they stop n times per year and add on the amount of interest there is right there. Continuously, we do not see that variable n. We don't say quarterly, we're going to stop 4 times a year and do it, or monthly. We don't see a word like that. We see continuously. This is the equation that you use for that. A of t is equal to P e to the RT. This equation is this equation. Let's just compare it. A of t is exactly the same. A sub 0 is the initial amount of whatever. In this case, it's called P, the initial amount of money, referred to as the principal. The same base, E, the growth rate, K, is replaced with R, the interest rate, R, and T is the same. Here, time is in strictly years. It wouldn't be counted in, you can use this equation. The time could be in seconds, hours, minutes, years, whatever. This, when we're using this, it's always in years. Okay, so this is what they say. How long would it take an initial investment of $1,350? So they tell us that P is this much money. They want it to triple. If it's invested at a rate of 2.6 per year, R is 2.6% or 0.026, and it's compounded continuously. So we can write the model. Let's do that before we try to answer our equation. A of t is equal to 1350 P e to the 0.026 times t. Now, if we did not even know the initial amount, they could just say, how much would it take for an investment to triple at this rate, compounded continuously, and you not even know the initial amount, similar to half-life. You don't even have to know the initial amount to figure out how long it takes to decay to half that amount. You could just simply say 3 times a sub 0. But since we do have that number, and we're saying triple, we're going to multiply that by 3. If it had said double, we would multiply it by 2. But we're going to we want triple. So we're going to say 3 times P. What does 3P equal to? 1350 times 3. We get 4050. 4050 is 3 times the initial amount. And so we're saying, we've got to solve for t. How long will it take to get this much money? So let's solve for t. Divide both sides by 1350. And we're doing that so that we can isolate the exponential expression right here, the e to the whatever. So we get 4050 divided by 1350 is equal to e to the 0.026t. Now that that's been isolated, we want to apply a logarithm. So take the natural log of both sides. Log base e of e to the whatever, these undo each other. So this is just equal to 0.026t. If I'm solving for t, I'm just going to divide by 0.026. And we get that t is about equal to the natural log of 4050 divided by 1350 divided by 0.026, and that gives us 42.25 or 42.3 years. It will take that long for this investment to triple. Okay, now let's look at 18 on your sheet. It says an amount A in a bank account after X years is given by this. So let me write down this equation. A of X is equal to so when they give you an equation and they have a different base than E, that's fine. Don't force it into that. You can just use what they give you, which is what they've done in this next example. A of X is equal to 450 times 1.06 to the X. A of X is 450 times 1.06. This is the base in this example, raised to the X. This is an exponential equation, and so this is one where they didn't use E as the base. That's fine. It says how much is in the account after 2 years. To figure that out, you would just simply substitute in 2 for X. And so we'll put in our calculator. And then B, how much is in the account after 20 years? Well, you would just simply put in 20 for X and put that in your calculator. And we will figure out that. So that's how we're going to do those. And then it asks, after how many years will there be this much in the account? So this is for part A, this is for part B, and part C, they say after how many years. We're trying to figure out what X is, but they told us how much is going to be in there. So we'll say 2,300 is how much we want to have in there, is equal to 450 times 1.06, and we're solving for X. So that's what we're going to do for part C. So first, let me just stick that in my calculator. And when you're dealing with money, always round to 2 places because of pennies. We just go down to the hundreds place. So just, nobody has to tell you that. You just know when you're talking about money, how far to round something. So we start here. 1.06 raised to the second power, and I'm going to hit enter and then multiply that by 450. And I get $505.62. 505.62. All right. Now for the next one, 1.06 raised to the 20th power times 450 gives me 1,443. 1,443.2109 and 21 cents. So that's the answer to that one. Part C. They said, how long would it take to get this much in the account? So we have to solve for X, which is an exponential. It's in the exponent. So first, isolate the exponential expression. Isolate 1.06 raised to the X by dividing both sides by 450. And so we get 2300 over 450 is equal to 1.06 raised to the X. We need to introduce a logarithm, an inverse. The choices are base E or base 10. I've been doing a lot of base 10, so now I'm going to do base E for this one. So I'll do natural log of this guy. So natural log of this, natural log of that. This does not undo each other because this base is 1.06 and this base is E. But it's helpful because we can use the power rule. So throw X in the front. So over here, we get the natural log of 2,300 divided by 450 is equal to the X times the natural log of 1.06. Now to solve for X, I'm just simply going to divide both sides by the natural log of 1.06. And we'll figure out that X is equal to, all right, here we go, the natural log of 2,300 divided by 450, and then I'm going to divide that by the natural log of 1.06, and I get 27.998 or 28. It takes 28 years. If we had to write a sentence, which you may well have to write a sentence, that's why I keep showing you how to write a sentence. You might have to say, it would take 28 years for an investment of $450 to grow to $2,300 in value. Okay, let's do the last one and then we'll be done. Number 20, it says the concentration of bacteria B in millions per milliliter after X hours is given by this equation. So this is another exponential growth situation. The base is E in this case, so it's very much like this. Okay, so let's see. What do we see here? It says B of X. Instead of A of T, they have B of X. That is fine. B of X stands for the amount of bacteria after X amount of time has passed. And so let's just take note of the amount of time. It's in hours, not years. So this is growing quickly. The concentration of bacteria B in millions per milliliter, after X hours is given by this. B of X, the concentration after X hours, is equal to 1.33 E to the 0.015, no. It's just 0.15. E 0.15 times X. Okay, so what can we observe here? B of X, what does it represent? The concentration of bacteria in millions per milliliter per hour, okay? X is in hours. What is the initial amount? The initial amount right here is 1.33 million per milliliter of bacteria. All right. Part A, how many bacteria are there after 2.5 hours? Part A is very simply, you're going to figure this out by putting in 2.5 for X. Part B, how would you figure that out? How many bacteria are there after 8 hours? You would just say, I'm going to substitute in 8 for X and figure that out. Part C, it says, after how many hours? This time we don't know the time. We are trying to figure out what X is. Will, after how many hours will there be 31 million bacteria per hour? This time they gave us the amount. 31 million per milliliter is the concentration. And we have to figure out X, how much time has passed in order for it to get to this concentration level. All right, so let's just finish this one. This is 1.33 e to the 0.15 times 2.5. This is 1.33 e to the 0.15 times 8. Okay, let's put this in our calculator. And let's see, 1.33 times e raised to the 0.15 times 2.5 is 1.935 millions of bacteria per milliliter. That's what that means. If we had to write a sentence, after 2.5 hours, the concentration has grown to 1.935 millions per milliliter. After 8 hours, the concentration has grown to, let's see what that's going to be, 1.33. E raised to the 0.15 times 8, 4.41 or 42 if I round, let's see, I'll go to 3 places like I did here. 416 millions of bacteria per milliliter. After how many hours will it take for this concentration to grow to 31 million per milliliter? Isolate the exponential expression by dividing by 1.33. So we get 31 over 1.33 is equal to e to the 0.15x. Now that the exponential expression is isolated, apply an inverse. You are allowed to use natural log, so I'm going to apply a natural log of this is the natural log of that. Log base e of e to the something. These undo each other. So you get the natural log of 31 over 1.33 is equal to 0.15x. It's now just a linear equation. We divide both sides by 0.15, and we get that x is equal to the natural log of 31 divided by 1.33 divided by 0.15 is 20.99. So to the nearest hour, let's say, it would take 21 hours for the concentration of bacteria to increase to 31 million bacteria per milliliter. Alrighty.